Many thanks again, Richard, for agreeing to do this session. And I'll hand over to you.
Okay, thank you, Rosemary, and thank you for inviting me to give this seminar. So as Rosemary said, I'm from the University of Greenwich. In particular, I'm in the Natural Resource Institute, which is located in Chatham, in Kent. But we are part of the wider university. Had a long history in overseas development, but also more recently has been working on in UK sector, European sector as well. So the title of our talk is Importance of Removing Field Heat from Fresh Produce. So this really stems from a project that Innovate project that we had called Coolberry, which was looking at removing the field heat from strawberries. I'll give you a bit of an introduction, first of all, about the Produce Quality Centre, who I work for, and then as part of NRI, and then I'll go into the project particularly in detail. So the next slide, and this is what's called the Produce Quality Centre. So this is actually a collaboration between ourselves and Natural Resources Institute at Greenwich, based in Chatham, the top arrow, and NIAB at the East Morning site. So this is a centre where we collaborate on research. We are centred around a storage building, which is called the Jim Mount Building. It's been present there for over 30 years. Its main thrust of research is in controlled atmosphere storage. Traditionally, that has been working in apple and pears, and we support the apple and pear industry into looking at new regimes for new varieties. But that's also extended the last sort of 15 years into other commodities such as field veg, brassicas, root crops, as well as potato and soft fruit. So we've sort of widened our remit, particularly over the last sort of 15 years, to try and help various aspects of the industry in terms of improving the storage life of fresh produce. So this building, it's got 10 stores. So we have up to 10 refrigerated stores, 6 large ones, and 4 smaller ones. Most of the downstairs of the building is larger stores, which contain various chambers, which allow us to work in controlled atmosphere research. This is where we're able to manipulate the atmosphere, so we can take down the oxygen to level the concentrations around between 3 and below 1%, and in some cases elevate the carbon dioxide concentration to anywhere between 1 to or even 10-15%, depending on the commodity we're working on. And we have up to 70 of these chambers, so it allows us quite a lot of flexibility in doing large-scale trials, which sometimes we need for we're doing sort of empirical work for the fresh produce industry. We also have some more modern chambers, which on the top right-hand side is a thing called a pod. This was developed part of another Innovate project looking at how we can measure in real time the respiration rate of fresh produce, and also allows us to also manipulate the atmosphere inside to levels that are below 1% oxygen, which is quite a risky episode you're doing if you don't have the right sensing technology. Allows you to avoid any anaerobic respiration. So these chambers allow us as researchers to take the oxygen levels down to less than 1%, even down to 0.4% oxygen. But we test the fresh produce as to the tolerance to low oxygen levels, and then if we start seeing anaerobic respiration occur, we can raise the oxygen level slightly, and that allows us to really extend the storage season of, in this case, apples, particularly by taking the fruit respiration down and then keeping the fruit pretty much on a life support system throughout the year. We can check that continually, check the response to the content, the fruit, to the atmosphere it's being stored in. So that's and we have various sizes of chambers. We can do sort of large scale 80 kilogram chambers through to sort of smaller scale 4 or 5 kilogram. And these chambers also can be put into commercial storage facilities. And currently, as over, especially it's an Anglo-American invention, and we've been working with the American states, and we have over, I think, $400 million worth of apples stored in these using this chamber technology. So it's been quite successful. In the bottom left-hand corner, we have a a chamber which is a bespoke cooling chamber. This allows us to do blast chilling of fresh produce, but in a very controlled manner, so we can actually get feedback mechanisms of measuring the fruit temperature or project temperature, and actually get a feedback that can then control the speed of cooling within that chamber. So it's been as part of an Innovate project, again, that allowed us to do some quite innovative real-time measurement of fresh produce quality. Okay. And then the outputs of this, we work closely with the fresh produce industry in general, but we produce some charts and recommendations. So this is just an example of the work we do in terms of CA, controlled atmosphere storage of apples. We produce periodically sort of recommendations to growers on different varieties and under different temperatures and how long they can store their fruit for. So sort of physical output that we do, and this goes to all growers as part of an AHD, as the AHD was remit. So I'm moving on now to talk a bit about the real thrust of the talk I was offered for this seminar. This is really looking at the need for rapid cooling of fresh produce. So I'm sure we all know, those who are working in the fresh produce industry, it's really important to, once you harvest fruit, get that fruit or vegetables, get that product as cool as possible, as quickly as possible, to extend the shelf life of that product, because fruits are respiring all the time. Fruits and vegetables are respiring, just like us. They're taking in oxygen, giving out CO2 as part of their natural metabolism. And once you detach that fruit, vegetable, leaf, bud, flower part off the plant, it then loses its source of moisture and nutrients, and therefore will start to lose moisture through respiration and transpiration. So in order to reduce that, getting the fruit cold as quickly as possible helps to mitigate some of the deleterious effects of harvesting the product. And that can be through benefits can be through reducing moisture loss. We can see it limits the changes in the surface color. You get less shrivel. It reduces decay further on, and also reduces the metabolic activity. And we'll show you a bit of that later on. I'll show you a bit of that in terms of respiration rates. So not all products behave the same. Produce behave the same after harvest. So this little graph on the bottom right shows you some examples of some of the products I work on: strawberries, cherries, and apples. Strawberries having a relatively high respiration rate and are particularly perishable, and they need to be cooled as quickly as you can. And there's also the mantra that every minute matters, after harvest, and trying to get the field heat removed. But I know I've probably got a lot of vegetable growers on the call here, so I just did some graphs of some data from published data. And actually, if you look at the respiration rate of some pretty familiar commodities there, that's respiration rate of things like asparagus, broccoli, kale, spinach, watercress, sweetcorn, are actually far greater than strawberries. They're actually, the metabolic activity is very high, and that underpins the need really to make sure that when these crops are harvested, that we are getting the field heat out as soon as possible after harvest. I know there's a range of technologies out there: ice cooling, vacuum cooling, hydro cooling, that helps growers do that. But yeah, these are very high respiration. I mean, you could also add peas in there too, but peas will follow the asparagus respiration rate. So this is really sort of, and more importantly, at increasing temperatures, the respiration rate increases. So ambient temperature of 26 degrees, you have very high respiration rates, and then until you get that product quality temperature down, then your respiration rate will continue to be high. So and then if you look at these are more, say, the medium producers. So these sit within the sort of strawberry range. I was talking about beans, Brussels sprouts, carrots, bunch carrots that with bunches on cauliflower and onions. They are still fairly robust producers of respiration, and still need to be managed robustly after harvest in terms of managing the temperature cool down. So going back to the project we were working on, was called Coolberry. It was looking at how you can firstly understand what the needs are of the industry, and then designing several sort of cooling rigs that went into the field to help manage the cooling operation. Now, so what we did in the first instance, we did like a 3-month audit of commercial farms to look at what was going on in terms of the farm picking activities, the post-harvest handling, how long the actual fruit were kept on the headland before it got sent to the pack house, as well as, you know, how long it took to cool the product. So we had somebody who was measuring temperatures of strawberries straight out of the picker's hands, then when it sat on the trailer waiting to be moved to the pack house, when it arrived at the pack house, and then after it had been chilled, and also the time it took to get to the various points. So it we built up quite a big database really of looking at, you know, understanding the sort of behaviour and how of the farm and various farms we looked at. And, you know, there's quite a variability there in terms of how long it took product to get down to the chilled temperature. Anything up to anything as quickly as sort of 1.5 to 2 hours, up to 4.5, and sometimes a bit longer than that. So that depended a lot on, you know, the rate of picking, availability of staff to transit the product back to the pack house, daily fluctuations in that. So, but it underestimated the need that, you know, actually, you know, there is a dwell time in the farm headlands of product which we could be eating into in terms of making sure the product is cooler quicker. And one thing we did, we actually then tracked all that temperature data, and we actually looked at the deviation. So this graph, these dots, blue dots, show the deviation of the temperature that was taken after the fruit being picked, the temperature when it arrived at the pack house. This is a plus or minus the temperature that it started off at. And in general, I mean, sometimes the temperature dropped below what it was harvested, but mainly the fruit temperature rose between 0 and 4 degrees, and sometimes slightly higher. And one or two thought outliers around 14 degrees. But that shows you that, you know, this dwell time on the headland, you know, is impacting on the quality of that fresh produce. And then we also then overmapped the daily temperature of the in the orchard. It's over a 3-month period, May, June, July. And what we found was actually that sometimes the biggest deviation wasn't actually on hot days. On the hot days, sometimes the fruit was taken to the pack house quite quickly. But on cooler days, we found that there's actually more of a dwell time when temperatures rising more on cooler days, but relatively. And that may be because it took longer for the fruit to be picked, because of less the cooler temperatures maybe preceding that might have affected the flush of strawberries that were being picked, so it took longer to pick. Or maybe people just thinking, well, it's not so hot today, maybe I've got a bit longer to get it to the pack house. But nevertheless, we're seeing, you know, deviations in temperature, mainly positive deviations, so fruit will get more exposed to higher temperatures. So then looking at the packing operation in more detail, so this is very typical of many farms we visited, that, you know, there's lots of crates. Crates are stacked. You know, the crates are have very little gaps in crate to crate, because I want to get as many crates of strawberries on that pallet as possible to improve the efficiency of transporting that product back to the pack house, which is very understandable. But inside this crate, and there's something particular to soft freeze, that they pick the fruit into punnets, which is not true of all fresh produce commodities. So inside those punnets, you also have plastic. Sorry, inside the crates, you have plastic punnets, and that then, in effect, if you have no gaps in the trays, produces pretty much a wall of plastic which the cooling has to cool. The cooler has to cool through. So this has a bit of an important sort of understanding, is that those punnets change over the course of a day, because punnet sizes change with picking supermarket demands. So you might start off with a punnet that has a bit of air hole gap between the below the tray, but if that tray changes, demand changes throughout the day, you might have a higher tray, which then there's no basically air holes to allow no movement of air through that tray, side of that tray. And when you get to the glass chiller, the pack house, you're basically trying to cool a wall of plastic, you know, and that can take sometimes 2.5 hours in old coolers to get that fruit down to temperature, where it should really only take half an hour and 40 minutes if everything was optimum. So this is a bit of understanding about, you know, how you should look at tray design and punnet design, particularly as part of this whole project. So going back to this, so we had this very innovative blast chiller built in our facility. It allows, so it's glycol cooled, and it allows, it has probes inside that feed back to the actual cooling mechanism. So it takes temperature of the fruit by sticking probes into the fruit, It also takes the air coming off the trays as a second measurement of temperature, and we can then use that data to feed back to the cooling unit to then monitor the rate of cooling. So we don't undercool, we don't overcool. So it allows sort of fairly bespoke cooling measurement activities. And then we were measuring the fruit temperature at each level, each tray, and also airflow as well, across those trays. And so one thing from that, and so we also measured the quality of the fruit coming out of those cooling cell. One thing we first looked at was actually what is the impact of those delays on the fruit quality. So if we delayed fruit by an hour, 2 hours, 3 hours, 4 hours, what did that have impact did that have on the fruit? We looked at several different varieties. In this case, we're looking at Morning Champion, and we kept fruit at ambient for 25 degrees, and then placed it in the cooling chamber every hour. And then at the end of that time, we measured the fruit respiration rate using, we have a rather bespoke chambers for measuring soft fruit respiration. And what we found was, as you might expect from the data, showed that every hour you delay, you get a rise in respiration rate, sort of peaked around 3 hours. And then after that, it sustained sort of same level of respiration. So that indicates there are sort of metabolically, the fruits are metabolically active, and actually that we are interfering with the fruit's metabolism by keeping the fruit warmer for longer. And then when we drill down, looked at different attributes of the fruit quality, not just respiration, but we looked at bricks, which is sort of a standard measure looking at sort of soluble solids, the juice quality. We didn't see a huge amount. We saw a slight dip in soluble solids after about three hours, but it wasn't consistent. We saw a sustained increase in weight loss, albeit small, but over a pallet that would actually add up to a few kilograms of weight. When we start drilling down into looking at the individual sugars, what we did see is sort of drop off in things like sucrose, sucrose particularly, and the pool of fructose and glucose started to drop off after about 4 hours. So you can see some changes happening metabolically, physiologically, as we extended the period of time when fruits were kept at ambient. Interestingly, the acid content, the citric acid content, didn't change over this period of time. We might expect it to. And then we looked at some sort of changes around weight loss again. Another way of looking at it is in this sort of a box and whisker plot. So what we found was that even after 1 day after we cooled the fruit, so we put it into a 2.5 degree store after we cooled the fruit, you can see the changes in weight loss happening and the variability. So every hour you basically left the fruit at ambient, you saw more weight loss and more variable weight loss between the consignments, and that also manifests itself after 3 days. So most of that weight loss did occur actually the first day of storage. So it just underpins the need to manage that temperature control as well as one can. And then looking at red color, this is a way of measuring sort of colorimeter looking at the red color of the fruit, and that also declined. This value is the higher the value, the darker the red. And as fruits were kept in a delayed in cooling, then the red color declined. And then, but also when we put fruit into shelf life, we saw the end of 3 days of shelf life at 17.5 degrees, that rots were appearing, and they were more obvious the great length of time the fruit were kept at ambient prior to cooling. So again, it underpins the importance of getting fruit cool as soon as one can. And then looking a little bit around crate design. So one of the things we were looking at was how does the crate impact on cooling, and can we optimize that for different punnet scenarios? So we basically measured the internal fruit temperature, which is the blue line, as it dropped. The external fruit temperature, we had probes on the fruit surface, and we also had temperature probes measuring the internal chamber temperature. And what you saw is the external temperature of the fruit cooled pretty quickly and in line with the air temperature, but as you might expect, the internal temperature took time longer to actually reduce. And we basically drew a straight line through the internal temperature data to get just a straight line metric to try and compare cooling rates between different tray and punnet designs as a sort of a metric. So what you're looking here is the shape of the graph of that cooling graph comparing different crates. So just ones that some that had cut out sections on the side, some didn't. Some had handholds, some didn't on the perpendicular sides. We also measured the flow rates of airflow going through the trays. And what you found is no surprise really, is those that had cutouts of the side of the tray allowed for better airflow through them and cooling. Those that didn't were far less effective, and there's about 2.5-fold difference between the worst and the best. But that would also be impacted by the type of tray punnets were inside the trays. And so one has to be, we did this for several different scenarios. This was one of the most widely used punnets by the particular farm that we're using. It's just an example, again, these cutout trays where you have, in this case, we have some plastic punnets inside. There's a little bit of an air gap you can see, allows airflow through, and that effectively means top and bottom of each tray that's having some airflow through, which helps to cool. But interesting, this was a experimental punnet that we're using, which is a cardboard punnet, and it's actually taller than the standard punnets, partly because it needed a flange on the punnet to help aid sealing of that punnet with a film. But what happened there was that most of the air flowed through the tray, but because the punnets were tall, the cooling rate was actually less, because most of the air flowed around the punnets and not across the top of the punnets. Just sort of, again, something to be wary of when you're designing tray and punnet design. So the next stage of the project was to actually try and design something which would fit in the field. So this was JD Cooling, who were part of the project, and they came up with this trailer-based cooling system. It was a prototype from one pallet of strawberries or soft fruits. It had a diesel generator on one end. It had a glycol cooling system attached to the top of the rig, and a control panel. And then on the left-hand side, we have a cooling rig, which is a set of fans. There are 4 sets of fans in this cooling chamber, so that basically different zones. So you're able to cool each zone of that chamber independently, and at a rate which the fruit was cooling at. So it took a temperature of either the fruit temperature, we had probes that stuck in the fruit, or the air temperature of the tray, of the air coming off the back of the pallet inside that chamber. So it allowed you to start to change the cooling rate based on the fruit temperature. And as you might expect, most of the air would naturally flow above and below the pallet resistance, and then less through the middle. So we were able to push more air through the middle when we put it onto a variable function mode. And that was able to cool the chamber within about 40 minutes from ambient being around 25 degrees in a particular year. And the problem with strawberries is you can't hydrocool strawberries. I mean, I know some crops lend themselves to that technology, but for strawberries, you don't want to get anything wet. So it has to be forced air cooling. So this is a bit of an experimental design. So this is the cooler with different fans. We had basically 4 zones, zone 4 to zone 1. And then the pallet was presented perpendicular to that set of fans. 2 sets of stacks of trays facing the fans and 3 behind. And that then we use that as a standard design throughout a series of trials. We're looking at trying to understand how we use that cooling chamber most effectively. That include looking at the sort of the glycol temperature of the coolant going into the fans, as well as looking at what's called a temperature differential. So this is understanding if we set a differential of the air coming off the fans with the air coming off the fruit, if we set it fairly high, so a big differential, sometimes we can overcool the fruit, as in we can force too much air across the fruit, you get too much transpiration going on, moisture loss. If you set it, if you start to reduce that differential, so you start to set it so that the air temperature coming off the fans is not a few degrees lower than the temperature coming off the fruit, then you can start to maintain a more controlled cooling of that pallet. And so we looked at that. So we looked at trying to both look at, in this case, we're looking at cooling the fruit at this would have been at a -5 glycol temperature, but we changed the differential of the air coming off the fan and the air coming off the back of the pallet. And when you had a very tight control, so 0.5 degrees, then cooling took longer. The orange line shows the temperature of the strawberries at the front of the pallet. These are at the back of the pallet. And so you can see when you try and tightly control it too much, that there's actually quite big variability across the cooling across that whole pallet. But when you start to increase that differential to 2 degrees, the differential between the back and the front of the pallet is less, and that means you get more uniform cooling. And actually, one could say that actually you probably need to do 2.5 to 3 degrees to actually get them enough airflow through the pallet to cool uniformly. And so this is just some data which we looked at how quickly it took to reach cooling, or how much it took to cool. 75% of the actual target temperature. So it's sort of more of an engineering approach. Normally you do 7/8 of the temperature. In this case, we looked at 75% cooling rate. So we looked at different dry cold temperatures. We looked at the differential temperature of the air coming off the fan versus off the pallet, both 0.5 and 2. But we had -1 glycol temperature. We're being quite cautious not to want to freeze the fruit because it was very close to the actual fans, but it actually took a long time to cool that fruit, over 90 minutes to get, in some cases, to get the fruit cold, which was far too long. When we got the glycol temperature to -5, then we got this down to less than an hour, and sometimes 40 minutes. So this is sort of a learning curve for us as to what we could actually operate the actual rig on. And then it was sent out into the field then. So we did some experiments at the PQC, and then we sent it out to a commercial farm, and they ran it for a month or 6 weeks over sending fruit, both so a pallet of fruit through the rig, cooling rig, CPU, Coolberry unit, or we took, or they've also followed the temperature of fruit that went through the standard trailer-based shipment to the pack house, which is about half an hour away from the actual field. And what you can see was that we have temperatures at pick, the blue lines, and temperatures of the fruit when it's arrived at the pack house, which is orange. And with the Coolberry unit, thankfully, we managed to see the fruit was being chilled in transit. So it actually operated while it was in transit. And then the time it got to the pack house, about half an hour again, we managed to get fruit temperatures down to less than 10, 5, 6 degrees, and sometimes below 5. Whereas the temperatures arriving at the pack house with the ambient cooled, as you might expect, were ambient or a little bit higher than what we started at. And one of the benefits of actually having this is that when the fruit comes off the Coolberry unit, it can actually be picked. It can be packed straight away. But this fruit, which has to be cooled in the pack house, has a sort of couple of hours of time, and that can be quite important to pack houses when they're looking for fruit to pack. So this was quite useful bit of information. And then at this point, the farm did their own commercial tests, looking at the shelf life quality of that product at 10 degrees, 17 degrees, and they gave it a commercial score. So green, 3 being good, 2 being just about acceptable, and 1 being rejected. And in general, I mean, it wasn't totally clear cut, but certainly there were more rejections in this particular set of data than there were in the regular transported fruit. But again, there was actually some times where actually there was some degradation of quality, even in the Coolberry unit, even then. So it wasn't perfect as we might have expected. So moving on, the third, as most projects try to expand every year, the project, we went for bigger and better. We got a slightly bigger trailer. We arranged the unit, Shady Cooling arranged all the units on there. This time we had a tail loading device that it was, so one of the issues was that manual handling was going on. Manual handling in the field, so it's quite considerable, lifting and putting down pallet trays a number of times, which not only affects the sort of vibration damage, but also the weariness of the pickers having to lift pallet trays continually. So we put a tailgate on the back of the trailer that allowed the pallets to be loaded on that tailgate, and then pushed back into the cooling chamber. And then there was a traction chain that then pulled once it got onto the pallet, pulled the pallet into the actual chamber to the first stage initially, and cooled the fruit. And every time you push another pallet in, the traction chain would then pull the first pallet further back by 1 pallet load and carry on cooling. So this was unfortunately this happened all through COVID, so there were delays in getting the kit produced, and then in terms of what we could do in the field was slightly delayed, and also getting spare parts for it when the generator conked out. But yeah, so it was the same system. It could cool 3 pallets. certainly, one option with this was to actually have a system that stayed in the field. We basically just pushed rolled pallets in and rolled them at their end onto a refrigerated truck. That might be their option. This was just a prototype that you could keep in the take from the field to the pack house, but there may be other options out there. Unfortunately, we didn't get the final version until the very end of the project, and unfortunately, the generator blew up after about a month. Unfortunate, but the data we got showed that there were some benefits in terms of reducing the amount of disease that we found. The botrytis rots were lowered by having the fruit rapidly cooled rather than being left in the field for longer. So that was some sort of learnings, and unfortunately the project finished at that point after 3 years. But we made some good inroads into the project. Now, one little aspect again we had one aspect was trying to understand, could we find a better way of tracking temperatures in the Coolberry unit? We have been putting holes and probes into the fruit, which unfortunately, if they get marketed, you get somebody complaining about having a big hole in the strawberries. So we wanted to see if you could actually use infrared system to capture changes in the punnet of strawberries as they were called. And the rather ambitious idea was that we could have a small camera that went through, indexed each tray, or every so many trays in the pack, and on a robotic arm that would go around and measure strawberry temperatures. We didn't actually get that far. We had some challenges at the beginning trying to find a very small infrared camera that would work inside a cooling chamber and not be affected by the buffeting of the air temperature or the actual flow of air going across it. So we had to eliminate a number of cameras before we came across this one. We had a recessed camera. So yes, so that allowed us to do some measure the temperature of that fruit going forward. And what happened was you could actually produce little spots on each strawberry, so we could actually track both the whole punnet and also individual strawberries. So we can actually get a range of temperatures of the whole punnet. And a lot was done in terms of the back end of the analysis. So we had we had a guy from Scorpion Vision who was doing a lot of computational changes to the data coming out of the camera in order to sort of allow us to track those chambers quite nicely. So we then looked at how well can that actually can that temperature track the changes in strawberry temperature. So the camera, we looked at both measuring, so without the camera, so just with the external internal probes, we saw changes both in the external and internal temperature of the fruit as the cooling cell operated, going down, which was operating up to around 2.5 degrees eventually. And then we actually overlaid that with the temperature output of the corrected data from the infrared camera. And actually, by the end of it, we were doing quite well in terms of mapping changes in fruit temperature over time. So they felt that there was a potential for taking that forward. Unfortunately, the project finished at that point. But yeah, so that's really what the outputs of that project were. But I thought just as before we wrap up that there's obviously the veg growers are in there probably know that there are better ways of cooling vegetables in the field as well. So there's things like hydrocoolers. You can have mobile hydrocoolers in the field, but using cold water, and also vacuum chambers, vacuum cooling devices that will help you. But then there are issues with all types of cooling systems. Sometimes you get a spore load appearing in the hydrocooler that can spread some sort of spores occasionally, or the vacuum cooling you can sometimes get an excess moisture loss. So there were two other options which I know most vegetable growers are probably quite familiar with. It's just to sort of acknowledge that people in the Coolberry project that were there. So we had ourselves, Berry Gardens were helping us with fruit supplies. JD Cooling at the time were with us helping us with all the refrigeration technology. Scorpion Vision did the infrared camera, and Hanneke National were an engineering company that helped to design some of the equipment as well. So just two more slides. Just a sort of shout out, really. Just also, the PQC University of Greenwich is part of what's also known as the Crop Storage and Post-Harvest Solutions Group, which is includes ADAS and James Hutton, and also Cranfield, but also others to join. It's really just looking at how we can take crop storage research forward in the UK. So that's one thing. And then just to say thank you for your time. And open up to questions if you have any questions.
Brilliant. Many thanks, Richard. It's great, really clear slides. So there are a couple of questions in the chat, and I don't know, people feel free to ask them. So Janet, do you want to ask your question, or do you want?
Yeah, okay, yeah, right. I've got a couple actually, just to be paid. I've just typed another one. Right, the first thing is, some years ago I was involved with a DEFRA Link project, and one part of the remit turned out to be in order to reduce the loss of fruit to diseases, to look at dropping the temperature of the fruit as quickly as possible after harvest. This is with raspberries, and we went into cooling within the set sort of time scale that you've been looking at with the strawberries, but we were going down to 2 degrees C, and we found as a consequence of that we actually got considerably better shelf life, far less fungal infection, and generally, the quality of the fruit was improved. I just wondered, have you actually looked at raspberries yourself or not?
No, so I mean, those temperatures I showed you to start with, that was getting most of the field heat out. We did take it down to 1 degree after that, so it's just that we stored it. But no, we didn't do raspberries. We didn't have time then. We would have liked to have done that. But certainly, getting the field heat out as soon as possible does underpin the need. Quality is improved by doing so. But yeah, raspberries and blueberries would be the obvious choice for next step.
Yeah. I mean, one of the things we looked at was actually what growers were doing in reality, and the majority of them, the other problem was that they were storing them at 5 degrees after they cooled them, raspberries with strawberries at 5 degrees, and that was far too high. An interesting thing was, if we pulled the field heat out down to as low a temperature as possible, we then not only extended the shelf life of the product, but also if the temperatures then came up to say 5 degrees C, it didn't really have a big impact on that fruit. It still retained its quality, having pulled out that temperature, down to a lower figure to begin with. The other ancillary question I wanted to ask actually is fibre or board punnets. My impression is that they are far more difficult to cool. I mean, you've actually shown the problem of the height of some of the punnets, but generally I think growers are a bit concerned about actually getting the field heat out of them compared with plastic.
Yeah, you're right. I mean, I think once we tried that one, so we can only talk about that. That one had particular issues with the height. It was
yes.
But yeah, I think you need to have that space above and below the actual trays to to let that flow of air go through. So and if the punnets are narrower for any reason, then often you find the air it can go through the trays, still bypasses the punnets out the other side. So I think punnet design is actually quite important in terms of optimizing cooling, and the crates clearly. But I mean, the thing about the crates is that growers, well, they will change crates when they need to, but that's obviously not going to happen straight away until they sort of need to replenish the crates.
They're quite an expensive investment. That's the problem. And once you've got several thousand of them, you don't want to replace them immediately. Just my impression is that the sort of the fibre punnets are very solid, if you know what I mean. They don't. I mean, I presume with plastic you are getting a certain amount of, in the punnet that is, not the trays, but with between the punnets you're getting a certain amount of air movement and cooling because it's a relatively thin material compared with a new fibre punnet, which is more insulating, if you like, but insulating out the cooling.
Yeah, and I think also where the crates are orientated on the actual pallet also. I mean, it's not the limitation we can do, but certainly understanding that sort of air passage across the whole pallet is quite important.
Right. Thank you very much.
Great. Thank you. Gary, do you want to ask your question?
Okay, fine. Can you hear me?
Yes, I can.
Richard, thanks very much for your presentation. The three pallet unit was very interesting development. I was just concerned that if you only loaded 1 or 2 pallets into it rather than the full 3, whether there was a problem of air taking a short circuit through the side of the pallet rather than the air penetrating down the full breadth of the pallet. Is that a problem with that?
That would have been a problem. I think we were looking at, as always, projects. The best bits happen at the very end of the project. We were looking at sort of air curtains, a way of trying to understand ways in which we could sort of section off each section of that 3 pallet rig. And there were sort of discussions about, well, you can't put an air curtain across because you'll just knock the fruit trays off if one's going through. So we looked at sort of various sort of miniature curtains, or I mean, the other question was that you could also turn off, if the one wasn't working, we could turn off one of the we could either push everything through to the back and section it off that way. But we were looking at sort of high throughput sort of farms where they were turning over sort of 6-12 pallets in a couple of hour picking. So we didn't really get to the point where it was only half empty.
Yeah, understood. Yeah. Okay, thanks.
Great, thank you, Gary. Does anybody else want to ask a question? If you do, just put your virtual hand up and have a go. Oh, there's another one in the chat, which is Jazz. Do you want to ask that question, Jazz?
I think I did see the actual question. So it was blowing. So it wasn't sucking, it was actually blowing air across. I know some cooling systems sort of suck air through pallets or plenums, but this was actually pushing it through. And that allows us to sort of change the flow rate of air across different sections of that pallet.
Okay. Any more questions for Richard? No. Okay.
One more coming.
So is there another one coming?
Cooling grapes. No, it'd be great to do that. No, something we haven't done, but it'll be good to grapes.
Oh yes, sure. So there is. Yeah. Yeah.
Yeah, and we're happy to. I've got my details there, so if you need to contact me, I'll try and look at what we can do.
Yeah. Brilliant. Yeah. I guess the scope is very broad, isn't it, in terms of
I mean,
types of produce. Yeah. Okay, right. If there aren't any more questions, then just leaves me to say thank you very much indeed, Richard, for a very interesting presentation. It'll certainly, I'm a consumer of raspberries and strawberries at every time of the year, and there is amazing variability in the shelf life, which presumably that's one factor, if there must be others as well. But yeah, no, brilliant. And as I say, the next webinar will be on the 17th of February. So thank you everybody for joining us.